So the next type of function or graphs that we're going to look at are ones that have asymptotes. So here's just some random curve here which has got several asymptotes. But an asymptote, a way of describing the behaviour of a function at its extremity. So let's just draw them in. Different types of asymptotes that we could have. Okay, we could have vertical ones. Now, the formal definition there, it's going to occur if the limit as x approaches a of function x is plus or minus infinity. As I say, that's a formal definition. What it's basically saying is the graph at a is going towards either negative infinity or it's going up to positive infinity. Basically, we're talking about a gap in the domain. So our function will never touch or cut that vertical asymptote. It's an exclusion from the domain. And curves, I always say, bend towards the asymptote and go off to infinity and so on. We could have a horizontal asymptote. There's an example of one there. Now this is what happens out at the extremity. So the limit as y approaches plus or minus infinity of function x is equal to b. Hang on, y approaches infinity? That should be x approaches infinity, shouldn't it? Shouldn't be y approaches infinity. It's the x value, so just fix that up on your sheet there. That should be x approaches plus or minus infinity. So as those x values are getting bigger and bigger and bigger, this curve's getting closer and closer to the value of b. And then the other type we could have, oh good, that one says the right thing, x approaches, are oblique. So oblique are ones that are at an angle. And so I've got one in here, out here at the left. Instead of the curve going to a horizontal value, it's going to an oblique value. So it's actually going off to infinity. So the limit would also go to infinity. Now the thing is, oblique asymptotes are technically straight lines. You can have curved asymptotes. Actually, it's whatever function the curve's approaching. So it might approach a quadratic. That's fine. It's just what is the curve looking like out at infinity. So the usual ones we see are those vertical ones and the horizontal ones and occasionally oblique ones, but it is possible to have other ones as well. You can cut, and you'll notice my curve here does, you can cut oblique ones and you can cut horizontal ones. That's fine. Because the oblique and the horizontal ones are saying, what happens out at the extremity? What happens out at infinity? So over here, it's nowhere near infinity, so it's fine. Whereas the vertical one, it could never cut. I guess the first type of asymptote you saw was with the hyperbola. Or to give it its more correct name, the one that we've seen before, is the rectangular hyperbola. It's called the rectangular hyperbola because the asymptotes are at right angles to each other. So that's why we call it the rectangular hyperbola. And so the most common one we've seen is y equals 1 on x. Or another way of writing is xy equals 1. Now just like the straight line displayed direct variation, so if we were to plot our data and we're wondering what sort of relationship exists, straight line would be a direct variation. A hyperbolic one like this would be inverse variation. As one gets bigger, the other gets smaller, and vice versa. There you go, that's what I was saying before. Rectangular hyperbola have the two asymptotes that are perpendicular. And once again, just like all the other functions we've seen so far, we can create all the different rectangular hyperbolas and other hyperbolas for that matter, using translations, rotations, reflections of the basic one, 1 on x. How do I recognise it? Well, if I see one variable is on the top of the fraction, I mean technically that's y over 1, and one's on the bottom, then I've probably got some sort of hyperbolic function happening. So that's the key I'm looking for there. See some pronumerals at the bottom of a fraction, I've probably got some sort of hyperbolic function going on. The other one that we see a fair bit is the exponential. That also has an asymptote. Okay. So, whoop, there's our basic one, which I've called a to the power of x. But as I've mentioned there, the base will also determine the shape. The base here with this standard one is bigger than 1. So if it's bigger than 1, it starts very shallow and then gets steeper and steeper and steeper as we go along. If the base was between 0 and 1, it would be the other way around. It starts very steep and gets shallower and shallower and shallower. Well, how do you recognise this one? This one's a bit easy. Oh, look at that. There's a pronumeral in the power. What's it doing there? So it's in the power, or to give it its technical name, exponent. Hence why we call it the exponential. So we get our exponential shape. Yeah. The base has to be positive, not equal to 1. 1 to the power of x is a very boring curve if you think about it. Just straight line, because 1 to the power of anything's 1. So there's the first bit of theory today. Not a lot of questions to do on these, but we'll have a look at that.